Okay, so here's what we were talking about last time. Just a quick reminder. So we're talking about this idea of diagonalization. Ultimately, now diagonalization comes from a broader idea. That is the idea of similarity. Remember, we talked a lot about this idea of similarity. It's kind of a weird concept. It's defined, at least in terms of how the book writes it down, which I'm very happy with. It's defined with a conjugation. Trouble with a conjugation is it's, the good thing about a conjugation is it's algebraically very crisp. There it is. No question as to exactly what that means. Trouble is it's a little bit opaque. So the first big step to make when you're talking about similarity is to make the connection that similarity, when it comes to matrices anyway, means you are simply talking about a change of basis. Right? So a conjugation means I was looking at a linear transformation with respect to one basis. Now I want to reconceive of the same linear transformation. We're not changing the linear transformation. We just want to think of it with respect to a different basis. Okay, so with that in mind, diagonalizability, similarity to a diagonal matrix, can be thought of as saying that the matrix you're talking about represents a linear transformation that you're just looking at the wrong way. That better, you should reinterpret the linear transformation given by A in terms of a different language. Think of it in terms of, let's say, the V basis instead of the S basis, from which point of view the matrix is actually diagonal. Okay. All right, so ultimately that's the big picture I want y'all to have for what it means for a matrix to be diagonalizable. A matrix is diagonalizable if you're just looking at it from the wrong point of view, and then from the right point of view it's actually a diagonal matrix. Okay. All right. Don't forget we had all this discussion of language. This is just to put your mind at ease about certain bits of language. This used to really bother me, the idea of taking a matrix and changing it, and then claim that even though we've changed it, all we've done is put it into a form. Well, what's it? Right? Is it still it if you have in fact changed it? So the way we resolve that linguistic contradiction is to realize that what we're talking about really is not the matrix. We're talking about how the matrix represents something underlying that's more important that we are actually interested in. When you're talking about row reductions, you don't really care about the matrix. The matrix is just your foot in the door toward what you really do care about, which is the set of solutions, set of homogeneous solutions. Right? When you're talking about diagonalization, the purpose of the matrix is really just as a tool to help you understand a linear transformation. Okay? And the process of putting it into a form then, the idea is that we want to preserve the things we're actually interested in. These processes don't affect the things that we're actually interested in. And these forms then are just really kind of the better, the more efficient, more convenient way of describing the things that we're actually interested in the first place. Reduced row echelon form is just a more desirable way to represent the solutions you're interested in. And by analogy, what we call diagonal form is really just a kind of a more convenient way to represent your linear transformation. Same deal. Okay. Alrighty, so we did a numerical example last time. This came out of left field for no apparent reason. I decided that I was going to take a bunch of eigenvectors and use those as the basis to do a change of basis. No apparent reason. Right? And we went through all the details and computed this matrix, one column at a time. And lo and behold, look at this. We got a diagonal matrix. How nice. Right? And then I tried to persuade y'all, at least numerically, notice the pattern. Doesn't it feel like this should always work? That this is no coincidence. This will, in fact, always work. The last thing we talked about then was a proof. And this is that proof. So just a quick reminder, if a matrix is diagonalizable, there's what it means for a matrix to be diagonalizable. By the way, let me scratch off the punchlines here. Diagonalizable means conjugate to a diagonal matrix. There it is. Right? What does it mean for there to be a basis? What does it mean for there to be a basis consisting exclusively of eigenvectors? Well, there it is. Right, if there is an entire basis for Rn consisting of eigenvectors, this matrix equation down here, taken one column at a time, just says these vectors, when you multiply by A, you get multiples of those vectors. Right, so this single matrix equation is simply a way of saying that all n of these vectors are eigenvectors. So proving this result, proving that diagonalizability happens exactly when you have a basis consisting of eigenvectors, simply means that I've got to figure out how to get from that algebra to that algebra and vice versa. And it ends up being pretty easy algebra, right? You just, take this matrix here, whip it over to the other side, observe that that's a section 1.2 application of matrix multiplication that I have here in red. The algebra is pretty straightforward, right? But the punchline is what we care about. So this is where we ended last time. Let me take a quick pause. Does anybody have any questions before we go on? Okay. All right. Okay, I want to show you another proof of this fact, not because there's anything sketchy about this proof. This proof is highly satisfactory. But proofs do two things. A proof, on the one hand, establishes truth rigorously, right? And that's a very important purpose of a proof. Another purpose of a proof, though, is to give you a point of view on a line of reasoning, an understanding of a perspective on a statement. So this offers, I think, a very nice and crisp perspective on the theorem that we're making here, that diagonalizability happens exactly when there are enough eigenvectors to make a basis. That's nice. But there is a different point of view that I like. Now, this next proof that I'm about to show you is not in the book. I think it's very cool, though. I want to encourage you to, think about this point of view in addition to the one on the previous page. Again, we're going to start with exactly what does it mean for a matrix to be diagonalizable. All it means for a matrix to be diagonalizable is that thought of with respect to a different basis, the underlying linear transformation is diagonal. Right? This is that other point of view we had. This isn't the conjugation point of view on diagonalizability. This is the change of basis point of view on diagonalizability. Okay, so what can we do with this? The linear transformation, ultimately, that A represents. That linear transformation, what can we do with the fact that from a certain point of view, a diagonal matrix represents it? Keep in mind, we know some nice things about diagonal matrices. In particular, diagonal matrices have the feature that their eigenvectors and eigenvalues are free. Right? That you can just read them straight off. The standard basis vectors are always the eigenvectors. The corresponding diagonal entries are always the eigenvalues. Real easy to write down. Everybody on board so far? Let me point out I haven't really done that much. I've written down the definition, an alternative point of view on the definition of diagonalizability. I've got a diagonal matrix to work with, and I've made a really easy observation about that diagonal matrix. Okay. All right, so here's the point of view I wanted us to take at this point, and that is, you may recall we spent a bunch of time last week at some point looking at statements about matrices and trying to figure out, okay, how should I think about this statement, and what does this statement say in a different language? What language is being spoken here, and how can I translate into a different language? So let's play that game. What language is being spoken here? Well, the matrix goes from V language to V language. And what that tells me, the fact that this is the incoming basis language for D, the fact that that's script V, tells me that this is representing something in script V language. Right? Okay, so what do these coefficients represent in script V language? Said differently, what do you get when you take this linear combination of those vectors? you get VI, right? These are the coefficients of VI, written as a linear combination of those vectors, one of which is VI. So, easy observation there. We made an observation much like that back in the previous section. Oh, I guess it was 2 sections ago. Okay. Analogously, what about on the right hand side? What about the vectors that are coming out here? Well, again, what this matrix D being what it is, the output language is script V. So this thing here represents something with respect to that same basis. What does that represent? Well, same basis, same coordinates, same result. Right. So taking this point of view, this kind of, what's the language and how do I interpret from that point of view on this statement, I realize what languages are being used and can therefore realize that this statement here is just saying that T of VI is lambda I VI. Right, so I'm taking the what you might call the script V interpretation here, and I'm just writing it sort of basis free. It's a statement about abstractions. D is just a way of talking about the linear transformation T. Those coefficients up there, interpreting in the same language, are really just ways of talking about VI. So let me remind you, what's happened so far in this proof. We've interpreted diagonalizability as telling me that in a certain language we have a diagonal matrix. Diagonal matrices have easy eigenvectors and eigenvalues, and that statement about eigenvectors and eigenvalues translates very nicely into a statement like this. At which point we're almost done. Let's just say this now with respect to the standard basis. Well, don't forget, the whole point to this, the original matrix represents T with respect to the standard basis. So that is standard basis language for the same thing. All right, so let me go. So here again we have one of these situations where we have 5 statements that all say the same thing. That's saying it with respect to the script V basis. That's how you say the same things with respect to the standard basis. And notice eigenvectors. Right, this is exactly what it means for these vectors to be eigenvectors of A. And so we are done. The matrix being diagonalizable, it follows that basis consists entirely of eigenvectors. So take your pick. See, whichever one of these proofs you like better. I encourage you to take a little bit from both. I do really like how this proof here is. This is very crisp, right? This is it's pretty bulletproof, right? Very short, hard to argue with, very satisfying in that sense. Arguably, though, maybe you could say that it's a little light on intuition. This proof here, different proof. Maybe this is a little bit harder to swallow, a little bit harder to digest. It's good practice, I think, in this certain point of view that I'm pushing on how to think about all this change of basis business. But ultimately, there is something very intuitively satisfying about this argument. Once you've fully digested this argument, it sort of points out that, ultimately why diagonalizability has to do with eigenvectors is because diagonal matrices have obvious eigenvectors. Pretty much. Okay. All right. So anyway, like I say, not in the book. I hope you'll find that useful. Okay. So a little bit of a summary of what's happened. We've talked about diagonalizable matrices. A matrix is diagonalizable if it is conjugate to a diagonal matrix. Don't forget, conjugate means sorry, my stylus. Conjugate means this little construction where you multiply by an invertible matrix on one side and its inverse on the other side. So diagonalizable means conjugate to a diagonal. Don't forget conjugate means change of basis. Change of basis for a linear transformation means that this is a change of basis matrix. Here, let me do it like this. Change of basis matrix. And don't forget a change of basis matrix has the feature that the columns represent those vectors. Of course, with understood with respect to that basis, that being the standard basis. So it's those vectors. Okay. So quick summary of how everything lays out and fits together. So don't forget these formulas right here. The diagonal matrix and the diagonalizable matrix are related by conjugation. Students very often have trouble with the, is the exponent of -1, is that on the left or is that on the right? And I think it's a mistake to try to memorize your way through this. Don't make the mistake of thinking, oh, it's on the left when you've got D on the left, or something like that. Because this notation for how we represent P in the first place, just writing it as P, it's not immediately clear what P is. Which way does P go? Does P go from V to S or from S to V? Right? So this can be confusing. Let me point out to you how you can resolve these kinds of questions every time. Right? This will always work. And that is, you've got something like this written down, and you're trying to figure out, oh gosh, does the inverse go there, or does it go there? Which way does it go? Oh, is P from V to S or S to V? Or very confusing. Write down what you know about the specific matrices that you're relating. D, the diagonal matrix. That is representing T with respect to the basis of eigenvectors. That you know for sure. That's always the case. That's the punchline of both of the previous two proofs. Right? The original matrix, certainly in this case, one could imagine in general, that original matrix represents the same transformation, thus the idea of diagonalizability. We're talking about the same linear transformation. Let's say with respect to the standard basis. You know these two facts. You know A is that, you know D is that. And I claim this forces you to make certain choices about this other matrix. The standard basis, this being the input basis for our matrix on the left, well, that's got to be the input basis then that goes into the product on the right. Here, let me do it like this. That's got to be the same as that. Likewise, that, here, let me do this in the other green. That has got to be the same as that. The language that is the output language for this product on the right, well, that's got to be the language that's the output language for the matrix on the left as well. So those are both S's. And then analogously, whatever is going to go into here, well, that better be the same language that comes out of there. Ditto over here, whatever is going to go into there, that better be the same language that comes out of there. Excuse me. So just by looking at this conjugation equation, you know exactly where the V's are and exactly where the S's are. So specifically, that's got to be S, that's got to be V. Let's see, that's got to be V, that's got to be S, and therefore, let's see here. So therefore, the one that's from V to S, that's the one that I would probably naturally call P. Or, let me say that a little bit differently. Assuming that's the one that has been called P, I see it, there it is. And then analogously, this thing here, that's not from V to S, that's from S to V. That is going exactly the opposite way as the one that we're presuming would be called P. Okay, so with this sort of approach, it doesn't really matter, if in the context at hand, if for whatever reason the matrix that's been given to you is maybe it's not called P, maybe it's called Q, and it's the change of basis matrix backwards. Right? You don't have to remember which one goes where and that kind of thing. Write it down. Think it through. The bases will tell all. Right? The pieces have to fit together. Okay. All right. Okay, so here's, let me go back now to our big theorem. Here's what we just proved. Diagonalizability is the same as saying that we have a basis for Rn consisting of eigenvectors. So a really nice punchline. Diagonalizability, we're going to see when we get later on and start looking at some differential equations, we're going to see that's a really big deal. It's very important. So, next question. How can I tell under what circumstances will it be that I actually can find a basis consisting of eigenvectors? And so let's explore that idea a little bit. When will I have an entire basis consisting of eigenvectors? So going down to this observation here, we wrote down some algebra kind of like this back in section 5.4. Counting eigenvectors, how many eigenvectors do you have? Don't forget that for any given eigenvalue, you never get more than the multiplicity. There's no promise you will get as many as the multiplicity, but you will never get more. The multiplicity is an upper bound on how many eigenvectors you're going to find. And that applies, across the board for all of the eigenvalues. Of course, we also know that the multiplicities add up to n, and therefore the grand total number of eigenvectors less than or equal to n. So, in this case, then let's re-ask our question. How could we have an entire basis for Rn consisting of eigenvectors? If we're gonna get a basis for Rn consisting of eigenvectors, we need n eigenvectors. We need a best case scenario, right? We need for nothing to go wrong. We need to get, in other words, equality in all of these cases. We need to get the maximum possible number of eigenvectors for every eigenvalue, no exceptions. And in that case, we will just barely have enough eigenvectors to make a basis. Everybody see that? Here's a little sticky business that turns out to be fine, but I feel like I got to say it. There is a question of, if you take the eigenvectors that you have for each eigenvalue, and if you do throw them all together, in the way that we sloppily do when we talk about, grand total, how many different eigenvectors did we find? Does it follow that the resulting sort of collection of all eigenvectors is independent? It's just a matter of working it out. It turns out the answer is yes. So check. If you want to see that proof, it's in the book. It's not something that I think you necessarily need to worry about. It's just a bunch of details. But anyway, acknowledged and not a problem. Okay. All right, so the big question, do you have enough? Are there ever any missing eigenvectors? That's what it all comes down to. So let's look at our first case. Think back to the very beginning of 5.4. That was sometime last week. And remember, we factored the characteristic polynomial like this. This factor gave rise to an eigenvalue with multiplicity 1. How many eigenvectors did we find? Well, we found 1. So the multiplicity was 1. The number of eigenvectors, also 1. We maxed it out. We got the maximum possible number of eigenvectors for that eigenvalue. Okay. This factor, eigenvalue is 4, multiplicity 1. How many eigenvectors did we find? Also 1. Right, so again, we maxed it out. For that eigenvalue, we got the maximum possible, namely the multiplicity, namely 1 in this case, maximum possible number of eigenvectors. So, since we maxed it out in the case of each eigenvalue, we should have, in fact, a basis for Rn consisting of eigenvectors. Let's think that through now. Wait a second. This is n equals 2. We have 2 eigenvectors, and that will be a basis for R2. And it's fine. Okay, so this matrix, that original matrix that we wrote down, diagonalizable. Okay. let's take a pause on this before we go on. Any questions about what happened there? Everybody's good? So remember, the point is diagonalizable happens if and only if you have a basis consisting of eigenvectors. A basis consisting of eigenvectors happens if and only if there are no missing eigenvectors. And, well, in this case, there were no missing eigenvectors. Okay. All right. On the other hand, there's this little sad story here. You remember this matrix with this characteristic polynomial. And let's look at those factors there. Those factors give this eigenvalue of 1 with multiplicity 2. Right. The multiplicity there you see is right there. So, in order to not have any missing, if you will, eigenvectors, we need to have 2 eigenvectors here, but sadly, we don't. Sadly, here we get only 1 eigenvector. So you might say there is a missing eigenvector. We did not get the maximum possible number of eigenvectors. We don't have enough eigenvectors. So thinking it through again, we don't have enough eigenvectors to make a basis. There's only 1. 1 vector cannot be a basis for R2. Right? We don't have enough eigenvectors. We don't have a basis consisting exclusively of eigenvectors. Therefore, per our theorem, this matrix is not diagonalizable. Which is bad news. This is going to lead to headaches when we get into Chapter 6. There is a differential equation of sorts that relates to this matrix, and diagonalizability would have made that differential equation a lot easier to solve. And since it's not diagonalizable, it's not going to be easy to solve. So this is bad news. Everybody on board? Okay. All right. Okay, I'm going to show you a couple of quick applications here. I'm not going to spend a lot of time on these applications because really these aren't the applications that we really care about. These are kind of quickies, little easy ones that I can throw out there. They're all kind of connected to each other. But let me just remind you that the big application, the big punchline for all of this business about diagonalization is that it's going to help us solve differential equations. So we're going to see a very powerful application in Chapter 6. So that is still coming. But there are a couple of easy little freebies that I'll go ahead and show you now. So here we go. Don't forget this matrix. We've done a lot with this matrix. We found its eigenvectors. We found its eigenvalues. Don't forget, furthermore, that when a matrix is diagonalizable, we have these conjugation relationships. This is a change of basis matrix, and it has columns that consist of the eigenvectors. Right? So, with that reminder, this matrix, the eigenvectors are these columns, the eigenvalues are these diagonal entries. Don't forget the inverse goes here. Right? So this is our our change of basis. This is our diagonalization of that matrix from the point of view of change of basis. And note the prominence of the eigenvectors and the eigenvalues. Okay, so example of things we've already talked about. So what does this buy us? And I'm going to speculate. Suppose you want to raise this matrix to a really high power. Now, you're probably thinking, okay, we'll have the computer do it. Well, okay, sure, right? But computers are much better at arithmetic than we are, sure, right? But that doesn't mean that they can just instantly do all arithmetic, right? I mean, there is a significant amount of arithmetic that goes into multiplying matrices, and if you want to raise this matrix to the power of 10, yeah, sure, the computer jumps all over that. But if you want to raise this matrix to the power of 100 trillion, that's a different story, right? Okay, so here's the clever observation to make. If D is a conjugate of A, then A is a conjugate of D, like so. Then A squared is just A times A. Matrix multiplication is associative, so you can sort of group your parentheses like this. P inverse times P is the identity. You can scratch those off. And what we've ended up with then is that a power of A is a conjugate of a power of D. Now, I just wrote this down for A squared, but I claim that something very analogous happens if you're looking for, let's say, A cubed, right? In fact, I can just append on here. If I wanted to write A cubed, there it is, right? A times A times A, and these factors cancel just like that, and likewise these factors cancel the same way. And notice that right next to each other then you have D times D times D, and thus D cubed down here. So this pattern holds. Well, this is kind of a neat deal. Now, how do you capitalize on this? I mean, what's the payoff? The payoff is that this arithmetic here is much easier. Multiplying a diagonal matrix times itself so many times. Pretty easy. In fact, here it is. Right? You want to take the diagonal matrix and raise it to the nth power, just raise the diagonal entries to that nth power. That's it. Right? There is no sort of linear combinations of rows and columns. It's diagonal, so the arithmetic is easy, freebie. So if I want to raise this matrix here, if I want to raise that matrix to a crazy, crazy high power, yeah, there's a lot of arithmetic involved, but alternatively, that's super easy. And then I've got a trivial, multiply by that matrix, multiply by that inverse matrix. That's trivial, drop in the bucket, right? Practically nothing. So we've reduced a hard arithmetic problem into a much easier arithmetic problem. Everybody see how that works? Neat fact, right? Neat little application of diagonalizability. Okay. Here's a way to capitalize on that. So this is you might call an application of that application. I think most of y'all have probably seen Fibonacci numbers. They're kind of cute, right? And by the way, there's a million little applications of Fibonacci numbers to the golden ratio and petals on flowers and all sorts of situations where Fibonacci numbers show up. Interestingly. Okay, they're defined as follows. A given Fibonacci number is the sum of the two previous Fibonacci numbers. Starting off with 0 and 1 as our first two. So with 0 and 1 as our starters, the next number is 0 plus 1, which is 1. After that, this number, 1 plus 1, is 2. 1 plus 2 is 3, etc., etc., etc. Y'all can do the arithmetic. Okay, so the question then is, what's a formula for the nth Fibonacci number? Now, obviously, I suppose if you wanted to compute the, 75th Fibonacci number, you can just keep going. Just compute them over and over again, right? And that's fine if you're computing the 75th Fibonacci number. What if you're computing the 100 trillionth Fibonacci number? That's much harder. Again, too many calculations. Right? Okay. Here's the clever trick. I wish I thought of this. I didn't. Somebody showed me this trick. Here's the really clever idea. Notice that instead of thinking of the Fibonacci sequence from a recursion relation on the entries, you can instead think of it as a recursion relation on consecutive pairs of entries. So those two entries you can compute from these two entries. Oh, do it like this. By multiplying by this matrix. It's just a matter of directly observing, right? I mean, this says the n plus 1 Fibonacci number is, the sum of the two previous. Okay, that's what we had before. The second equation seems trivial and pointless and like a waste of ink, right? But the nth Fibonacci number is the the nth Fibonacci number. Effectively, the second line of that doesn't do anything. Right? Nevertheless, there it is. Equivalent formulation, right? Fair enough. We've successfully turned an easy relation into a less easy relation, seemingly having accomplished nothing. Here's why we care about that. What we can do then is apply this recursion relation in different times and show that if you start with what you might call the first consecutive pair, then you can get to the nth consecutive pair by applying n times. Said differently, I can compute an arbitrary Fibonacci number by raising this matrix to the power of n. And we just got through talking about that on the previous page, right? If I want to raise a matrix to the power of n, that matrix, you just got to find the eigenvectors and the eigenvalues, diagonalize, and celebrate, pretty much. Before we get into those details, I'm going to pretty much gloss over those details. That's a great application for y'all to do. Please do that. But before we get into that, let me just show how will we finally do this. I claim that what we're looking for then, this nth Fibonacci number that we're looking for, it's clearly the bottom entry of this product. There it is. Right? It is furthermore the left column. It comes from the left column of this matrix to the nth power, because that's what multiplication by 1, 0 does. That 1, 0 picks out the left column of that matrix. So we are looking then for the bottom left entry, bottom left entry of a to the n. Okay. So the details, like I say, are exercise for y'all. This matrix, eigenvectors and eigenvalues. There they are. Fill in those blanks. Notice I'm using this shorthand G to represent the golden ratio. The arithmetic of the golden ratio is weird. It allows you to rewrite and simplify things in nice ways. So, for example, let's see if I can remember this correctly. So, 1 over G is the same as G minus 1, if I remember correctly. And I think, well, anyway, let me not speculate on the other. I want to say G squared is like G plus 1 or something like that. So some weird little relations. Anyway, taking advantage of those relations, simplifying appropriately, there's your eigenvectors, there's your eigenvalues. You can see the eigenvectors, these eigenvectors, you can see here as the columns of the conjugating matrix. You can see the eigenvalues, as the diagonal entries. We're raising to the nth power. Remember, diagonal matrices raised to the nth power. You just raise the diagonal entries to the nth power inside the conjugation, like that. And it's mostly all over except for little details. One little quick time saver is to notice that this number here, negative 1 over G, is less than 1. So if you are computing with this formula a very high power, like let's suppose we're trying to compute the 100 trillionth Fibonacci number, right? Well then, that number to the power of n is crazy small. It's round off error. You can throw it away and not be off by much. Certainly there will be only one integer that's anywhere close to what you will be at when you round that off, right? So good thing to do is just round that off. Admit that you're finding an approximation. Multiply all this out. Look at the bottom left entry as we previously discussed. And here's your formula for your nth Fibonacci number. It's a simple computation on the golden ratio. And by the way, notice as well, immediate consequence of this, Fibonacci sequence is approximately exponential, where the ratio is the golden ratio. Okay. So I think it's a great exercise. I want to encourage you all to do this. Fill in the blanks in this example. Make sure that you can think that through. And here's the result that you're aiming for. Okay. Questions before I go on? Everybody good? Okay. Lastly, I don't have any details in this example. This is just kind of a a template, you might say, for who knows whatever applications. Sometimes, if you're dealing with a physical system, some sort of contraption that you engineers might concoct, right? This system might take values in stages. Like it might not be a continuous system where the parameters describing the state of the system are continuously variable. It may be that they take a discrete set of values here, and then in the next stage there's a different set of values, and then in the next stage there's a different set of values. And that's not a continuously passing time, but sort of a time taking values in sort of discrete steps. So if that's the case, it could be that the state of your system, whatever values it is that describes the state of your system, relate to the previous values describing the state of your system by way of a matrix. It might not immediately look like that, but it could be that if you redefine your numbers, maybe the actual parameters are these numbers plus or minus different constants, or maybe the logs of these values, something like that, right? If you can find a way to take the parameters describing your system, look at the relations between them, and write them in this form, then what you have is a tool for predicting the future state of your system. So specifically, if a matrix represents the succession from one state to the next, m to the k gets you from the first state to the kth state. Right? And if you want to know that kth state, then what you really want to know is how do you raise a matrix to a large power? And of course, that's discussed a couple of pages back. Writing a matrix to a high power is much easier to do when the matrix has been diagonalized. Okay. So anyway, like I say, this isn't a specific example. This is kind of a template for examples that you might find in your futures. So look for opportunities where to possibly capitalize on this. Okay. All right. So 5.5. We are now halfway done with section 5.5. As I mentioned before, it's a really big section. There's a lot of stuff in here. The next thing in section 5.5 is a tough one to talk about. So it's called Jordan Canonical Form. It's going to take us a long time to get through. What is Jordan Canonical Form, and why should I care about it? And how can I make it useful? So again, you got to kind of bear with me here. Short version of that question is, it's the answer to this very reasonable concern. We have already established that diagonalizability is good. If you can diagonalize, good things happen. We're going to see even more of that when we get to differential equations. If you have a differential equation that's described by a diagonalizable matrix, solving that differential equation is not hard. It's pretty straightforward, actually. So what if the matrix isn't diagonalizable? We know that sometimes they're not. We've seen an example. We can well imagine that plenty of circumstances where there just aren't as many eigenvectors as we were hoping. Jordan Canonical Form is your consolation prize. It's not what anyone's asking. No one's hoping for this, right? But in the case where your matrix simply is not diagonalizable, sorry, the consolation prize, good news, is that you definitely can put that matrix into something called Jordan Canonical Form. So Jordan form. And let me remind you, when I say putting the matrix into the form, I mean by way of change of basis, aka conjugation, aka similarity. So this is this is in that conversation of we're interested in understanding a linear transformation. The linear transformation is our underlying object of concern. I allow change of basis and similarity because I know that doesn't change the underlying linear transformation that we actually care about. Just like I was thinking when I was trying to diagonalize. So in that process, I can't necessarily get to diagonal form, but I can always get into this thing called Jordan canonical form. Okay, now, so that's the role that it's going to play in our story. What is Jordan canonical form? It's a bunch of rules. And it's got certain things in common with reduced echelon form in that sense. You may recall the very first time that we saw reduced echelon form, it was a weird set of rules. Right? Well, Jordan canonical form is an even weirder set of rules. It's going to take me a couple of pages just to tell you what the term means, Jordan canonical form. So here we go. We're going to start with something called the eigenvalue block structure. By the way, there's a sort of a chemistry of Jordan form. Let me remind y'all how chemistry works. There's molecules, but then inside of molecules, there's atoms. But then inside of atoms, there's, protons and neutrons and stuff, right? I mean, so you can there's a high level structure, and then a medium level structure, and then a low level structure. And I suppose, depending on if you're talking about particle physics, that you can talk about what's inside of a proton and stuff like that. Okay. So there's kind of something along those lines that happens here. I'm going to start with the large-scale structure. I like to call this the eigenvalue block structure. So here's the big idea. Jordan form consists of a bunch of blocks. I have to zoom out, I suppose. Here we go. So there's a bunch of blocks right there on the diagonal. So the corners of the blocks are exactly on the diagonal. When I say there are a bunch of blocks, what I mean by that is it's all zeros outside of the blocks. That's super news. Zeros are awesome, right? Zeros represent convenience, right? Okay, so lots of zeros there. But there's some neat things you can say furthermore, by the way. Looking at one of these eigenvalue blocks. For example, let's look at the first eigenvalue block. That first eigenvalue block, the diagonal entries are the first eigenvalue. How about that? And the multiplicity of that eigenvalue tells you the size of that eigenvalue block. So there's a very strong connection between what I'm calling eigenvalue blocks and the eigenvalues. In some sense, a lot of the defining characteristics of this block come from the eigenvalue. The diagonal entries are the eigenvalue. The size is the multiplicity of the eigenvalue. That's why I call them eigenvalue blocks. I think that's a reasonable choice. Side note, the book doesn't give a name to these blocks, which I think is weird. I think these are of sufficient importance that they deserve a name, so I made one up, eigenvalue block. Okay. All right. So, large-scale chemistry of Jordan form. What we're going to do now is we're going to now look inside of this eigenvalue block. See what's inside of there. What's the more detailed chemistry. So here's that eigenvalue block again. What is there inside of an eigenvalue block? And, well, more blocks. Also on the diagonal. These are called basic Jordan blocks. So blocks inside of blocks, which is a kind of a strange arrangement, but that's how it is. More good news, all of the entries in here, inside of the eigenvalue block, but outside of the basic Jordan blocks, all zeros. So again, super news. Zeros are awesome. Zeros represent convenience and stuff I don't have to worry about, right? So it's a good thing. Okay. Exactly how many basic Jordan blocks are sitting inside of an eigenvalue block is a topic for another day. We won't have time to get to. The very last thing I'm going to be able to talk about here is in these basic Jordan blocks, just looking at the basic Jordan blocks. Now, so turning up the magnification on our chemistry just a little bit more inside of a basic Jordan block, such as that one. It's always the same structure. Keep in mind, we're talking about a block on the diagonal. We've already agreed that the diagonal entries are the eigenvalue. So the eigenvalues are on the diagonal, and the only other non-zero entries are ones immediately above the diagonal. Everything else is zero. And that's a pretty good place to draw the line. We'll pick up here next time and try to figure out what we can do with this and see some examples. See y'all later.